Welcome to the final stretch. I told you before we have 3 sets of notes left to cover this last unit of information. We're shifting gears one last time to talk about how electricity and magnetism work together. And so today we'll introduce electricity, talk about how it flows in a current and it flows through things called circuits, which you've already gotten a little bit of experience with in doing an online introduction. I will give you a little warning. As I loaded this onto my iPad, some of the slides got out of order because of the way I saved it on my computer, and I didn't bring my notes home. That is another copy of what you guys got, so I had to go off of memory, and I'm really hoping I got everything back in order the way it is supposed to be. So if it happens to be a little out of order, that kind of explains it. So just bear with me, and it'll be an adventure. So electric current is where we're beginning, and if you think about a current in a river, that's how I like to think of an electric current, just because a lot of us have been in rivers before, or maybe you've been into a water park where they have the lazy river and you can sit in a float and it kind of takes you along. So the current in terms of electricity is the flow of electrons throughout a material. So there's implied movement. This instrument called an ammeter is a device that measures the strength of a current, and the unit that we use for current is called amps, and this is short for amperes, and we're going to use a capital A to abbreviate that. Now, voltage, you may have seen signs like the one at the bottom here that says high voltage. The voltage is kind of like the power that pushes the current through the circuit. It's like the juice. I think I told somebody that in class today. So examples like would be batteries and generators. These things are creating the current. The unit we would use for this would be volts. And so an increase in the voltage means that you have an increase in the current. So the more I push something, the more it's going to move. And so that is a way we can think about it. The voltage is kind of the power source behind the current. Finally, another thing that comes into play in terms of how current flows through a material is something called resistance. And in a couple of classes, I compared this to the game Red Rover, which I'm really surprised to hear many people have not even heard of this game before. Some of you may have heard of it, but may not have played it, and honestly, it can get a little violent, so maybe that's why people don't play it anymore. But when I was a kid, when Miss Putnam was a kid, we remember playing this game with our friends. I used to play it with my youth group at church. I mean, it was popular, but basically you get 2 groups of people in teams, and they line up holding hands and spread out, and the goal is you want to call one person from the opposite team to try to come and break the chain of people. And so that person is running as hard as they can towards the other team, and they really want to bust through, because if they do, they can join the other team. If they don't, they're out and they're losers, which is unfortunate. So, if you want to play it sometime, it would be fun. Just try not to hurt yourselves. But I tell you that story and give you that example because the idea of trying to hold against a person running through the chain of hands is like resisting them. You're trying to keep them from moving between you or moving through you. So the idea of something resisting electricity means that it's opposing the movement of electricity altogether. So things that are plugged into an outlet would be an example of something that is causing resistance in electricity. It is blocking the flow, or it's using up some of the electricity before it's allowed to continue to move on. So the amount of resistance that is plugged into something that has electricity, we're going to use the measurement of ohms. And so it sounds like you're meditating. I know a lot of you make that sound, ohm. You're probably shaking your head at me, I know. And we're going to use another Greek symbol called omega. This is actually the last letter of the Greek alphabet. And it kind of looks like an upside down horseshoe. So this is the unit we use for this measurement. The more crowded with electrons that the circuit gets, the more resistance there is implied. So the more resistance there is, the less current there is. The more someone is holding on to each other, or two people are holding on to each other in the game of Red Rover, the less movement there's going to be in between them. Somebody's not going to be able to run through them. You can also think of this in terms of a dam being built in a river. The whole purpose of the dam is to block the flow of the water. And a lot of times we use this to store energy and use it for electricity in general. But the better the dam is built, the more strong it is, the less the current is going to be able to flow. So again, anything that you plug into a wall, into an outlet, would be an example of a resistor. So most common, what we'll talk about in just a minute, is light bulbs and any other type of appliance you might know. So the idea here is that current wants to take the path of least resistance. And you can think about being in the hallway between classes. I know when I was in school, I would get really frustrated with the people walking really slow or not paying attention to their surroundings. And so I would try to weave my way around the crowd and find any opening so I could hurry up and get through, because I just don't like big crowds. And this is the same type of thing that the electrons are going to do. As they're trying to flow from one place to another, they want to find the easiest path to take. So several examples of the path of least resistance include going through thicker wires. If it had the choice of going through a thicker or thinner wire, it's going to go through the one that has the more room to travel. They also go through wires that don't have blockages or openings, because if there's an opening in a wire, or if the wire is cut in some way, the electricity can't just hop from one end to another. It has to have a connection, because air in between acts as an insulator and it blocks the flow. It also is going to flow through any kind of conductor. We've talked about conductors and insulators back in the first semester when we dealt with like metals and everything. So metals are good examples of conductors, but insulators would be things like rubber, air, wool, things like that are not good conductors of electricity. So this guy that we have using his name for the unit of resistance, we named a law after him too, because he came up with the relationship between resistance, voltage, and current. I said that resistance is equal to the amount of voltage divided by how much current there is. And so we're going to put this in our triangle. We've been doing this all year, so that way whenever we come across a word problem, super easy. So we're going to put a V at the top here, and then an I and an R at the bottom. And if any of you are into racing, there's a motor speedway or racetrack down in Danville called VIR, and so this is how I always remember it. I actually had a friend that used to race go-karts back in college. You may be wondering what I is. So we have R for resistance, V for voltage, but there's no I in current. But the person Ampere, who we have named the unit for current after, was French, and so the idea of current, the word they use there is intensité. I don't really know if I'm saying it right, but that starts with an I, and that's why we use that for the abbreviation. So just to review, resistance is measured in ohms, voltage is in volts, current is in amps. Let's try a problem. A car's headlight is connected to a 12-volt battery. If the current is 4 amps, we want to know the resistance. So we're going to take R and divide our voltage by our current. So our voltage is 12. Our current is 4 amps. You should be able to do this without a calculator. 12 divided by 4. Say it out loud. Come on, do it. Good job, it's 3. And remember, we're going to use ohms for our unit. And it's that funky looking letter that looks like an upside down horseshoe. Alright, so circuit is the complete path that a current flows through. And this is all caused by the voltage. So voltage is coming from the power source, and this is where it's coming from. This is an example of a battery. And this picture is unfortunately awful right over here. It kind of gives you a key as to what these symbols mean. So what I just circled here on the picture is a battery. And then these straight lines would be considered wires connected to a battery. And every time you see this little squiggle line, that's a resistor. That's something plugged into the wire. We also have these two symbols to show if I'm trying to measure the current or the voltage, I could put an ammeter or voltmeter in. And these are symbolized by a circle with an A and a circle with a V in it. So let's take a look at the two different types of circuits, and then we'll move on to talking about what we're doing tomorrow. So two types of circuits, one is called series and one is called parallel. So many of you know I'm pretty much obsessed with Harry Potter or Narnia, basically like any type of series that's some kind of fantasy like kid book. I always really love those books. And if I want to read the books, it's, I need to read one after another. There's an order to it. I can't just pick up the fourth book in the Harry Potter series and read that for the first time and know what's going on completely without knowing the backstory. And so for series circuit, everything is connected in order. There is like one path that the current can flow through, and it has to hit one resistor after another before it goes back into the power source. And for a parallel circuit, you can think of this in terms of a ladder with different rungs. If I'm climbing up a ladder and one of the rungs breaks, yeah, that would be bad, but I can still manage to climb up to the next rung, assuming that it's not going to be too far away for me to reach. So for a series circuit, there's one path for the current to flow through. For the parallel circuit, there's more than one path for the current to flow through. So let's look at the left side of your table, where we have a couple of other things to fill in about a series circuit. If you take a load, that means a resistor, out of a series circuit, it opens the circuit up. That means that suddenly one wire is not connected to the other, and so that means that the electricity can't just hop over that empty space. It just can't flow anymore. And if the electricity isn't coming out of the power source and then back in on the other side, then the circuit is not connected. It's not complete. That means everything else that used to be connected in the circuit is going to turn off or it'll go out. So if we have lights, many of you might have had experience with the old types of Christmas lights where if one goes out, all of them go out, and you have to sit there and try to figure out which one of the lights went bad so you can replace it and make everything work again. So old Christmas lights are a good example of series circuits. The more lights that are added to a series circuit, the greater the resistance, so that means the greater the blockage is for the electricity. And so that means each light has to become dimmer because they're all sharing the same one path of electricity. On the right-hand side of your table, we have parallel circuits. And if I take a resistor or a load out of a parallel circuit, it doesn't completely open the circuit because there's another path for the electricity to go around and manage to make its way back to the power source. So everything else will still stay on. So that means if I'm working in my kitchen and I plug in my blender and my toaster or my refrigerator, several other appliances are also plugged in, the moment I unplug one of those appliances, the other things will still stay on. So that's the way your house is wired. It doesn't matter how many lights are added to a parallel circuit. They'll all receive the same amount of voltage because they have their own connection to the battery itself. So they would all stay the same brightness no matter how many you add. So last bit here, I want to practice identifying series and parallel circuits based on the pictures. So here's the battery in A, and I just want you to take your finger and trace the wire there. You should see there's only one path. So that one is series. Letter B, we have two batteries here, but I want you to just trace the paths that the electricity could possibly take. And you should notice there are several paths. That means that it's parallel. Letter C, here's the battery. Again, start at the battery, work your way around. You should notice how many are there? Only one path. That means it's series. Letter D, we have a battery here. Again, you can trace your finger. You should see that there are multiple paths, which means it's parallel. And finally, E looks very much like B, except there's just one battery. But still, it looks like rungs of a ladder, and there are multiple connections, so it's parallel. Tomorrow we'll practice this some more. We'll get some extra math practice with Ohm's Law, and make sure that if you have any questions, you write them down and bring them up in class. Look forward to seeing you tomorrow. Just 2 more sets of notes.